All right, well, welcome to part 4, SPHS chemistry, acids and bases. We're almost there. 5 parts, parts 4 and 5. Now this is the part that we've all been looking forward to, because now we start to get into some of the math of how do we calculate the H plus and OH minus concentrations in the acids and bases, and from that then how do we calculate the pH and the POH. Okay, I know that you guys love math, but you're going to need to have a calculator with you today. The good news is that with a video, you'll be able to go back and kind of look at the examples. But once again, if there's ever something that you don't understand, please feel free to contact your teacher and let us help you with that. So we're going to break this up into 2 parts with the math. We're just going to talk about the calculating H3O plus and OH minus first, because before we can get to pH, we have to be able to do this, because pH is based upon the H3O plus and the OH minus concentrations. So we already know that in an Arrhenius, now really all pH problems all just deal with the Arrhenius. We're going to be dealing with water, and we're going to be dealing with H3O plus and OH minus. So the Arrhenius definition is really the only one that we need to worry about from dealing with pH and all these math problems. Okay? Bronsted-Lowry, really, it's the conjugate acid-base thing that we just talked about that's important. But for now, we're always going to be kind of focused on the Arrhenius definition. Okay? Now, since everything takes place in water, we know water is neutral. Well, why is water neutral? Well, water isn't just pure water. Water undergoes what's called self-ionization. It actually reacts with itself and makes a small amount of H3O plus and OH minus. Okay? Now, it is very small amounts. Most of the water dissolves, or is just like this. Okay, it doesn't dissolve in itself. It just exists in this form. But some very small amount actually does react. So in any glass of water, you have some H3O plus and some OH minus. But notice that for every water that reacts, you get one H3O plus and one OH minus. So in pure water, H3O plus always equals OH minus. That's the definition of a neutral solution. H3O plus equals OH minus. So in pure water, we don't have much, but there's always some H3O plus and OH minus. Okay? So experimental data, goes through, and we find, like I said, it's only a small amount. 1 times 10 to the minus 7. 10 to the minus 7 is 1/10 millionth of a mole. Okay? That is not very much. Okay? Now we're going to be using these brackets. Anytime you see something in a bracket, like H3O plus in a bracket, that's the concentration of the H3O plus in terms of molarity. So in pure water, it's been experimentally determined that the concentration of the H3O plus is 1 times 10 to the minus 7. But again, it's 1 to 1, so the OH minus is also 1.0. Oh, this is supposed to be times 10 to the minus 7, and that will be corrected before it gets posted on Wednesday. Okay, and so we end up having these 2 things are equal. But so the most important thing is in any water solution, any aqueous solution, you always have some H plus, you always have some OH minus. They are inversely proportional to one another. As one goes up, the other goes down. But you always have some of each. So in any and all aqueous solutions, there's always some. Okay? In pure water, H3O plus equals OH minus, so water is neutral. But in an acid, H3O plus is going to be greater than OH minus, and so that's going to make it an acidic solution. So if the OH minus, though, is greater than H3O plus, that tells me that it's going to be a basic solution. Okay? So you're always going to have some, but they're inversely proportional to one another. Okay? Now, just a little side note. A lot of times we just ignore the water and just put H plus. H plus, H3O plus, you can use them interchangeably, synonymously. The H plus is attached to the water. The water doesn't change the characteristics of it at all. And so H plus, H3O plus are pretty much the same thing. So you see it a lot of times written either way. And so don't worry about that. We're trying to be consistent and use H3O plus all the way through on this. So here, this is just exactly what we just said, just in a graphical form. In pure water, H3O plus and OH minus equal one another. In an acidic solution, you have a lot more H3O plus, but you still have more OH minus. And then at a base, you have more OH minus, but you still always have some H3O plus. They are inversely proportional to one another. Now, in math, you guys learned that in an inverse proportion, X times Y is equal to some constant K. That's the mathematical. You learn things in math so you can apply them to real subjects like chemistry. Math is a tool that scientists create to be able to do science. I tell the math teachers that all the time, we joke, okay? So I'm just kidding, but that's really why we learn math, is so we can apply it into real situations. So X times Y is equal to K. Well, in this case, the H3O plus is our X, the OH minus is our Y, so it's always going to equal some constant. We're actually going to use K. We're going to use K sub W for the constant for water. Which means that anytime you multiply the H3O plus times the OH minus, it's always going to equal this constant, which is equal to 1 times 10 to the minus 14th. Now that is temperature dependent, but we're always just going to assume that we're at room temperature. We're not going to worry about how it changes with temperature. So KW for us is always going to equal 1 times 10 to the minus 14th. Now this is important. This is huge, because if you know H3O plus, then since you know this times this has to equal this, if you know H3O plus, we can very easily calculate OH minus. If we know OH minus, we can very easily calculate H3O plus. They're inversely proportional, but when one goes up, the other goes down, but they're always there. They're always present. So this equation right here is humongously important. Okay? So if you're taking notes, which I hope you are, you need to be this here, highlight this on, hopefully you've printed it out. If you haven't, highlight it on your phone screen, highlight it on your Chromebook screen, okay? That's a super important equation right here. We're going to be working with, that's what we're going to do the rest of this video right here. So, if I'm going from H plus to OH minus, I'm going to use the KW equation, H plus times OH minus. KW is always going to equal this. So, here's an example. Given my H3O plus is 1 times 10 to the minus 5 molar. What's the OH minus? Well, KW is H3O plus times OH minus. So OH minus is equal to KW. Just divide both sides by H3O plus. So OH minus is equal to KW divided by H3O plus. Now we just plug in. KW is always 1 times 10 to the minus 14. Okay? And then this is given in the problem right here. Now you're going to need to know how to do scientific notation on your calculators. We've learned with it. We did it in the beginning of the year. If you don't remember how to use scientific notation on your calculator, you've got to Google it, figure it out, ask a friend, something. I'm not there. We're not there to show you how to do it, but it's your calculator, but you need to be able to put scientific notation in and be able to get these values. Okay? So you're just going to be expected to know how to do that. So, it's going to be important. We have down here, just use your parentheses when you're doing this. Depends upon what calculator you have, whether or not you have to use parentheses or not. Every calculator is different, so you're just going to have to learn your calculator. That's going to be on you. You guys are, old enough, smart enough to be able to figure out how to use a calculator to do scientific notation. Okay? Now, here's another example. Given the OH minus. Now instead of giving the H plus, we're giving the OH minus, but everything's the same. Now we're going to divide both sides by H3O plus to find, by OH minus to find the H3O plus. And so now again, KW is always 1 times 10 to the minus 14 divided by the given OH minus. And then again, as long as you can put that into your calculator, it's a super easy problem. It's just X times Y equals K. You're going to be given 1. KW never changes. 1 times 10 to the minus 14. So you're given 1, just have to divide it in to change it. Okay? Now, we're not always going to give you the OH minus concentration as this. Sometimes we're going to give you the concentration of the acid or the base, in this case the base. But you can see it only has 1 OH. We want the OH minus concentration here, and this is kind of what we did with solutions when things broke up into 2. What were the concentration of the ions in solution? And so this is going to be basically for every NaOH, you're going to get 1 OH. So we went through and kind of showed you the basic calculation, but you can do all of this in your head. Whatever this is, that's going to be the same thing. It's 1 to 1. Okay? So if we know the NaOH concentration, we really just know the OH minus. Now, if that happened to be Ca, or let's say BaOH2, well, that's going to go to Ba2 plus 2 OH minuses. Okay? So if this is 1 molar, for every one of these, you're going to get 2 of this, so the OH minus is going to be 2 molar. The same thing is going to be true with a diprotic H2SO4. You're going to get 2 H pluses, so you're going to get SO4 2 minus plus 2 H pluses. And again, that's H plus, H3O plus. I didn't put the water in there, so it's the same thing, but you're going to get 2. So if this is 1 molar, this is going to be 2 molar. Okay? So we're only going to be dealing with strong acids and strong bases, which ionize 100%. So whatever this concentration is, you can figure out the hydroxide. Most of them are monobasic or monoprotic, and so whatever this concentration is, it's going to be the same as your OH or your H+. There are some diprotic and dibasic, and then you just multiply by 2. Okay? We're only going to be dealing with strong acids and bases to do the pH and the POH and all that stuff. So whatever that concentration is. So notice now here we're just continuing this problem. We know this is just a very drawn out way. It's saying that the NaOH concentration is 1 times 10 to the minus 3rd molar. Well, I automatically know, because it's 1 to 1, that that's my OH minus. Now it's a problem just like this one, where I'm given the OH minus and I have to find the H plus. Okay? I just had to do, really again, you can do this as a mental step, since we know it's 1 to 1, that the OH minus is there. But this is just working it out in math. This is just kind of explaining the whole relationship there on how to get from concentration of this to the concentration of that. Okay? It's a little overkill. So, just trying to help you out any way we can. So he's just now going through H3O plus. Now this is the exact same problem as what we just did before. Okay? Notice that the concentration of OH minus is 1 times 10 to the minus 3rd compared to the H plus 10 to the minus 11. It's an extremely high OH minus, which means this is a very basic solution. Okay? So, here's your comprehension checks. Just got to go through and do the simple math on these and just use that 1 times 10 to the minus 14th and just kind of go and convert. And then here, the only difference on these is we give you the HCl. Okay? Now pay attention down here. This is H2SO4. We just talked about that. So we need the H plus concentration. Okay? So be able to figure that out first, thinking about this right here. Okay? So that's all it is for this, this part. The math isn't too hard. You can do it. Okay, learn how to use your calculator. And again, if you have any questions, let your teachers know. Okay, that's the end of part 4. We're almost there. Only one more to go.